Hey guys, this is Sean with Alexander Math and Physics Tutoring, and today we're going to look at logarithms. Logarithms are a subject that a lot of students just sort of go through the motions. You need your calculator to figure out what they are, and most students don't really get what they are. So I want to figure out what a logarithm is by going back in time to the 1700s when mathematicians first started using them. Okay, so what are they? They're the inverse operation of an exponential. And so I've written down an exponential here, 100 equals 10 to the x. And up until this point in time, there's no maneuver we can do to both sides of the equation to get that x by itself. You know, there's nothing we can do. We're used to doing what you do to one side, you do to the other, which of course is true. But there's nothing we can do to both sides so that we get x equals something. Okay, now this example I gave, I hope you can just look at it and see that the answer is 2. Just from guess and check, because 10 to the power of 2, or 10 squared, is in fact 100. Okay, so what did they do before calculators? Well, mathematicians had a table of values. They basically looked up the answers in a book. And so we're going to pretend logarithms don't exist, and we're going to try and solve some equations just using brute force plugging numbers in. Okay, so I'm going to write down 10 to the x equals 1. What is x? Again, there's nothing we can do to both sides to get the x by itself, so we're just going to guess. So 10 to some power is 1. Well, can anyone tell me? What is 10 to the what power is 1? Well, in this case, we can know for sure, because anything to the 0 is 1. So that's the answer there. Now I'm going to say 10 to the x equals 2. Anyone know what the answer there is? Well, it's got to be bigger than 0, right? And it's got to be smaller than 1, because 10 to the 1 is 10, so it's got to be a decimal. And so we're just going to use our calculator to guess numbers here and plug in 0.1. If we did 10 to the 0.1, we get 1.25, too small. We could do 10 to the 0.2, which gives us 1.58, too small. We could do 10 to the 0.3, which gives us 1.99, and we're going to call that close enough. So x is about equal to 0.3. In other words, 10 to the power of 0.3 is roughly 2. What if we had 10 to the power of x equals 3? Again, we're going to plug in numbers. We're going to guess something bigger than 0.3. If I plug in 0.5, I get 3.16, so that's a little too big. If I plug in 10 to the 0.45, I get 2.8, a little too small. And if I plug in 10 to the 0.48, see, I'm just guessing here, I get roughly 3.01, which we'll call close enough. Do one more. Okay? And again, we're just plugging in numbers into our calculator until we get the right answer, but through brute force, we get x is approximately equal to 0.6. Okay, what am I doing here? Again, we're trying to solve these equations by brute force, plugging numbers in. 10 to the 0 is 1. 10 to the 0.3 is roughly 2. 10 to the 0.48 is roughly 3. 10 to the 0.6 is roughly 4. Now, what is it we're trying to do? We want to do something to both sides of the equation. Let's look at that first one. In fact, I'm looking at I want to find a function such that if I plug the left-hand side of the equation into this function, I have no idea what the function is, so I'm just calling it fn. And I do the same thing to the other side. I plug the right-hand side of the equation into some function. What I want this function to do is spit out x. When I plug 10 to the x in, I want x to spit out. Okay? I have no idea what the function is. I'm just kind of brute force making it some function where if I plug 10 to the x into it, and x comes out. Now, the next question is, well, what the hell is f of 1, right? We don't even know what the function is. However, looking back up here, we already figured out what x is through brute force, or guess and check, basically. So we know that whatever this function is, when a 1 gets plugged in, a 0 comes out, right? Because x equals f of 1. And remember, up here we figured out what x is already. It is 0. Okay, let's look at the second equation. 10 to the x equals 2. Again, we're making this magic function that we don't even know what it is. If we plug the left-hand side of the equation in, 10 to the x, and we plug the right-hand side of the equation into this magic function, we're brute force saying whatever this function is, what I want it to do is spit out x. So Now we are doing something to both sides of the equation. And of course, again, the question is, what the hell is f of 2? Because we don't even know what the function is. Except we kind of do, we know. Because by brute force, whatever this function is, we now know that when a 2 goes in, 0.3 comes out. See where I'm going with this? And so we're starting to get some points on a graph here. Okay, so going to the other one, 10 to the x equals 3. We apply our function, our unknown function, to both sides. And again, a 10 to the x goes in, and x comes out. We're just making it do that because we're crazy. And x is equal to f of 3. When a 3 goes in, we already figured out what x is. 0.48 comes out. And just skipping ahead to the last one, we know that x, when a 4 goes in, a 0.6 comes out. What are these? These are points on a graph. So going back to the beginning, 10 to the x equals 1. When a 0 goes into our magic function, excuse me, when a 1 goes into our magic function, oops. So a 1 goes in, a 0 comes out. Going to our next point, when a 2 goes into our magic function, a 0.3 comes out. When a 3 goes into our magic function, a 0.48 comes out. When a 4 goes into our magic function, a 0.6 comes out. Okay, good. So now let's graph this thing. And we'll have 1, 2, 3, 4, 5. And I'm going to make my y-axis, I'm going to make them 0.1, 0.2, 0.3, 0.4. Okay, so what do we have? A 1 goes in, a 0 comes out. That's a point on the graph, right there. Maybe I'll change color. Okay, when a 2 goes in, a 0.3 comes out. When a 3 goes in, a 0.48 comes out, so that's right about here. When a 4 goes in, a 0.6 comes out. And we could continue this. If we continued, obviously we could just keep coming up with numbers that we solve through by brute force. But what we'd see is, as we connect the dots, there's something that looks like this. Okay, and what is that? That is the logarithm function. Okay, and in fact, we're going to call it the logarithm base 10 function. Why? Because it solves functions of the type base 10. Okay, and this function here, that's what your calculator does. It, you know, if you basically your calculator just figures out, can take this to infinite accuracy, right? And if you plug the log base 10 of 6 into your calculator, it's going to go dot, 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 up to this function and point out a value somewhere over here. I don't know exactly what it is, but it's going to be like 0.6 something. Okay, and that's what the log function on your calculator is. It's to solve equations of the type 10 to the power of x equals something. Okay, any number you want. So I hope that helps you understand what the log base 10 function is. And now, one little quick point I want to make before I sign off here. You can imagine that if we had a different base, instead of everything here was 10 to the power of x, what if it was 5 to the power of x equals 1, 5 to the power of x equals 2? Would it be the same solution set for x? No, right? It would be different values of x that make these equations true. And that's what the log base 5 function is, okay? So I hope that demystifies logarithms a little bit for you, and I'm going to do another video or two on these coming up so we can really get into them. Okay, thanks for watching, guys. Take care.